Designing, manufacturing, installing, and maintaining the high-speed electronic computer, the largest and most complex computers ever built.
Hello. Welcome to the Building Better Systems podcast, where we explore tools and approaches that make you and us better programmers. I'm Joey Dodds.
I'm Shpat Morena.
Shpat and I work at Galwa.
Galwa is a research and development lab focused on hard problems on computer science. Today on the podcast, we're going to be talking to Leo de Moura. Leo is a senior principal researcher in the RISE group at Microsoft Research. He was one of the creators of the Z3 Theorem prover, which is a widely known SMT solver used for tons of stuff like program verification, model checking, all varieties of automated reasoning. And most recently, he's been working on Lean, which is this mix between a functional programming language and proof assistant that essentially makes it easy to write correct and maintainable code. So we're going to get into how Lean came to be, what its uses are, and who should be paying attention to it.
Yeah, and Leo, it sounds like, didn't know much about the core concepts of Lean when he started. So we'll talk a bit about what it was like to dive into this problem, not really knowing so much about it. And now that Lean's taken off, we're going to do a bit of a discussion about where it's being used. It's being used at Microsoft. We've used it at Galwa a bit, and it's being used elsewhere as well. We've got the math community and the machine learning community pitching in, and even just the regular old PL folks like us. And so it's going to be a really exciting conversation.
Yeah, let's listen in. All right. Thank you very much for joining us today, Leo.
Oh, thank you for inviting me. Happy to be here.
So you've been spending the last few years, I'm not sure exactly how many, working on the Lean Proof Assistant.
Yeah.
Although I'm not sure it started out being the Lean Proof Assistant. Can you tell us a bit about that project?
Yeah, we started, the original goal was to have a library for connecting with systems like FStar, Coq, Isabel, and so on. You'd have more expressive logics, right? I mean, my previous system was Z3 for first order logic, but these systems, they all have Coq and FSR have dependence types, and we want to provide better automation for systems based on dependence type theory, right? That's how it started, but its dependent types are really fun, and we quickly figure out that we want to have our own proof assistants. And now it became a programming language, right? I mean, our original goal was to have a library. Now it became a proof assistant. And now we want to have a programming language too.
So there's all these tools, the tools you mentioned, I think tools like I think you said Daphne. There's a lot of tools that basically call out to solvers. These are tools that either are programming environments or they talk about other programming languages and they try to do proofs about these programs. And it sounds like you're saying when Lean started out, it was meant to be a library that sits between those tools.
Yes.
And a solver like Z3, basically.
Yeah. We would probably re-implement some of the features we have in Z3, or customize them for dependence type theory. But one goal was to avoid this loss in translation problem that we have when we go from a system like FStar that has dependence types and we have to go lower to first order logic. That's what Z3 supports. And the other goal was to try to combine these two worlds, right, of automated Theorem proving, interactive Theorem proving, right? We wanted to have a smooth transition between these two worlds and provide this as a library for systems like Daphne that you mentioned, FStar, Coq is already a proof assistant, but it could benefit from automation like we provide in Z3.
So can I jump in maybe for folks? When we were preparing for this, we talked about interactive theorem proving, how lean differs, and just in general about maybe the value of proofs in general, and getting the benefits of proofs by using a programming language like Lean. So maybe to step back for people who might not have those dots or connect those dots right now. What's interactive theorem proving, first of all, and then how does Lean fit in with that or doesn't?
Yeah, it's a great question. Not all interactive improvers are based on dependence type theory, right? But they are all, you can view them like it's a modeling language. You can write problems. You can precisely state a mathematical problem in these systems or a software verification problem, right? And then you can interact with the system to construct a proof that this property holds or this theorem is true, right? Some simple proofs can be proved automatically, but in general, this is an undecidable problem. You would need human guidance, right? And it's not that different from programming, right? When you start playing with systems like Coq, F-star, Lean, you're going to see eventually, wow, this is like programming, right? And especially you are based on dependence type theory, proofs are programs, right? If you know, a proof by induction is like when you write a function by recursion, right? And this analogy, I think it's great. I mean, even though sometimes for computer scientists, I think it's great for teaching people about proofs because they see, oh, this is just programming, right? And for mathematicians, sometimes they have gaps in their understanding what a proof is. I met many top-level mathematicians. They say, wow, after I started using proof assistance, oh, now I understood this stuff. I thought I knew it, but I had only an approximation, right? I didn't really understand all the details, right?
So to just lay out the landscape a little more, your history before you worked on Lean was working in Z3, which is an automated
Yes.
I guess an automated theorem prover.
Yes.
You give it more or less big math problems or big software verification problems, and it sort of says, I'm going to just take what you gave me all at once, and I'm going to grind for, maybe seconds, maybe longer than the life of the universe, and eventually I'm going to give you back an answer.
Yes.
And that was, I think once you spend long enough with them, you start to learn, well, maybe this isn't going to solve all the problems I want to solve.
Yes.
And it sounds like you looked to dependent type theory as a way to maybe help people massage things a little more and to let humans step in and start to work on these goals maybe before Z3 carried you across the finish line or something like that.
Yeah, this is a good point. I think Z3, in our experience, the projects that use Z3 to find bugs were very successful. They're using it as a constraint solver. You have this big formula and you're trying to make it true, right? In a test case generation problem, making it true is to find the inputs for your program that you exercise some behavior you are interested in. We have many applications that were very successful at Microsoft using this kind of application, right? Where you're using Z3 as a constraint solver. But using Z3 as a prover, it's tough because the problem is undecidable. For instance, for finding bugs, you find a bug. If you didn't, it's not a big deal, right? And you can always unfold. You don't have to find inductive invariants, nothing like that, right? It's really push button, this application of Z3. But when you're trying to prove, the complexity keeps getting higher and higher. The system gets more and more unstable, right? I mean, sometimes you make a tiny change in your problem, it fails to prove. Sometimes it succeeds. You make a tiny change that is irrelevant from your point of view. Right? But this is a system that is based on heuristics, right? The heuristics are going to fail you. We are not solving undecidable problems in Z3, right? It's just engineering or optimizing. There are two aspects of Z3. In one aspect, you may create decision procedures for classes of problems, right? You say, oh, this class is decidable. I'm going to write a very efficient procedure. But there's another part that you have these undecidable fragments and it's full base of heuristics, black magic. It's not very scientific. It's an art, right?
Yeah, and if you saw me laughing there, it's because the team I work on has been spending our time trying to use Z3 and its relatives as provers. So I'm sort of intimately familiar with the challenges you face there. And then Lean was meant to. I say Lean was Lean is a way out of this problem where instead of throwing things over the wall, basically saying, "Hey, solver, figure this out for me," you get to do this guidance using programming, as you put it.
And if you saw me laughing, it was because I didn't understand 80% of that.
Okay, sorry.
I'm obviously I'm not joking, but that's I don't have my hands in this stuff day to day, so of course I wouldn't. But in general, this, I mean, dark magic or whatever you called it sounds about right to me whenever I try to kind of understand how some of these things work. And did I interrupt you, Joey? Were you gonna ask?
Oh no, I would say, like, in depth, even though maybe you didn't understand a lot of what went by, it's worth one of the things Leo is calling out is these tools feel like programming. So there's this crazy world of independently typed programming and proof assistance where there's this deep type theory that goes into things. And on the user end, when things go well, you don't have to worry about that stuff at all. I remember a tool, the Cock, which is a tool like Lean, it being described as video game like, and that you have this nice layout of the things you know and the thing you want to prove, and you just kind of take it one step at a time and figure out how to manipulate these things and massage these things to eventually convince the computer that things are right. So we have a lot of thanks to give to teams like Leo's team and the Cock team that take all this really hairy stuff, and at the end of the day let you see this expression of I'm just writing proofs, I'm just doing programming. So that wasn't really a question, but it was more it was expressing a lot of gratefulness. I'm curious, I wonder if we can even do a quick example of sort of what a vision of how Lean might be used by somebody who's interested in showing software correctness. So one of the goals that you really have for Lean is that it's usable as a programming language, as a general purpose programming language. We started off talking about proofs and solvers, but what Lean really is turning into, or what Lean is now, I think it's fair to say, is a language that you can pick up and write a fast program in. Yeah,
we wrote Lean. The new Lean is written in Lean, right? I mean, our current compiler is Lean prover is all written in Lean, right? And it's great for us. I mean, we have managed to improve the system a lot because the first we are users ourselves of Lean, right? And another thing is that it's easier to make the system extensible, right? We have a lot of engagement from the community. They write many extensions. And because you can use Lean to extend Lean itself, the community can move Lean in different directions, right? It's quite diverse. We have users that are mathematicians, pure mathematicians, and we have users that are computer scientists, right? And they have completely different ideas of what Lean should be. But if you make extensible systems, they can customize themselves, right? And they do it. It's quite funny.
So Lean itself is evidence, I'd say, that Lean can be used for the computer scientist types. But there's also been a really big, very large amount of interest from the mathematical community. And this is people doing real analysis and things like that, right?
Yeah. There's pure mathematicians, applied mathematicians use. I have sometimes a hard time communicating with them. There's this mismatch in our languages, but it's great. I mean, it's great to have users.
Definitely for a new language, absolutely.
Yeah.
And it's great to build a language that can be what you want it to be, in a sense. It's not easy to support both of these groups, but it sounds like a path forward is this extensibility.
Yes. That was one of the main motivations. I mean, Sebastian Ulrich and I, when we start designing Lean 4, one of the main motivations is to make it extensible. Because we know people want to move things in different directions. Everybody has a different idea of what this construct should do, and they can customize now for their own needs, right? Yeah, it's quite different. I mean, and I think also for us it's easier to communicate with computer scientists because we have been programming, right, for a really long time. The mathematicians are like, they're just now starting to use formal languages, right? We have been using for ages now, right, computer scientists, right? Every programming language is a formal language, right? I mean, and we have been using, we use it, we learn a lot, right? If you go back into the past, people would be talking about, let's use flowcharts, right? Nobody uses this stuff anymore for teaching or speccing a program, right? But in the past, people thought this was an amazing idea. Or using natural language, right? Let's create a programming language that is you write in English, right? It's a horrible idea, right? I mean, we learned it's a horrible idea. But in math, people are trying to do things like that today. I mean, and it's great. I mean, they can extend Lean in this direction if they want. Maybe they will succeed, right? I mean, we failed as computer scientists trying to create a language that looks like English, right? But maybe they will succeed.
Yeah, it's not so much a horrible idea than it is an impossibly hard to achieve idea, right? It's on paper, it seems great.
Yeah,
and the outcome would be wonderful, but it's definitely a harder thing than it seems to accomplish some of these things.
Yeah, so my understanding is that essentially some of the topics and some of the core concepts that ended up being implemented in Lean were new to you.
Oh, yeah.
So I think even something as core to it as dependent type theory. Is that true? And I'd be curious to kind of hear what helped with that learning. How did you get yourself up to speed? Because I would imagine that there's some people listening that are in the same position. And not only did you get yourself up to speed, but then you implemented a language that's proven to be very useful to some folks.
I didn't have any background in dependent type theory. It's actually a blessing because you don't know how hard the problem is, right? Ignorance is great. You think you can do it, right? You say, this should not be hard. I can do this stuff because you are unaware on how complicated things are, right? But it's great to have. I have many colleagues of mine. Joey mentioned F-star, and Nikhil helped me. Josh Gontier was Microsoft. I mean, he was a PowerCock user, right? He helped me a lot. Jeremy Avigad, he was an expert in Isabelle Proof Assistant. He gave me a lot of feedback, and he also was pretty good user of Coq too. I mean, he was amazing in Isabelle, pretty good in Coq. He could also balance the difference between Coq and tell me the difference between Coq and Isabelle. At the time when I started Lean, Cody Rule also helped me a lot. I think some of you may have met him. Having colleagues helps a lot. I mean,
I was gonna say, like mostly through people. You got up to speed with this.
It's they spent hours talking with me. It's great. I mean, it was basically try and error. There are actually good tutorials. I mean, another good. If someone is interested in dependent type theory, a really good tutorial was written by Andre Bauer. He has a blog. He has a small, tiny type checker for dependent type theory. I remember it was one of the first things I did. Okay, let's follow his tutorial. Let's implement this stuff he has there.
And I guess, to give a shout out to the PL community, like this is, if Leo comes knocking, maybe a lot of people will talk to them, but I don't think, given most of the people you described, I don't think that was special treatment for you. I think this is mostly a group of people that are really engaged with the student community and helping anybody that wants to learn. So this is something that's not, that can be achieved if you want to learn, and if you have specific questions. Definitely start with the tutorial, but most of the people that you mentioned are pretty open to collaboration and to helping everybody learn.
I'm not I was face to face in all these examples I gave you, but some of them are very active online. For Code Rule, his Twitter, I think if you start to engage with him, he will answer you questions. But I don't use this kind of Twitter. I don't even I have a Twitter account that I never use it, but I'm too old for this kind of technology.
You are on the Lean Zulip, I believe. So there is a way to engage with you around Lean if somebody's interested. Right?
Oh yes, I am, but I have a hard time with this stuff. I find it super distracting. I don't know. Sebastian Ulrich's much younger than I am. He works with the Zulip. His notebook is here. He has a screen with Zulip. The message is there. He stops, answers something, goes back, continues to program. I can do that. I need full concentration. I can't keep switching between text messages and programming.
I don't know about young and old. I've seen that fall all over the place, but it's arguable which one is better or more productive. Some would be on your camp squarely.
Yeah.
Well, yeah. It sounds like, and I think this is honestly worth diving into, because I would view you as a very productive person, and I don't think there's a lot of debate there. It sounds like we should chat about that after the podcast. Lean is a huge accomplishment, right? And I don't think anybody would like look back and say like, yeah, I could have done it in half the time, right? Like Leo's obviously spending way too much time on Twitter or anything like that. But it sounds like you know who you are and how you work well. And I don't want to like ask for the secret to success, but how do you work so well?
Well, do it, fail, do it again, fail, do it again, fail. This is the fourth version of Lean, right? It's the same thing with Z3. Some people may not know, but before I started working with Z3 with Nikolai Bjorner, I was in SRI working on Yikes. Before that, I was in ICS with Harold Ruas. We tried ICS. We didn't work so well. We started Yikes 1 with Bruno Dutertre. The first version was scrapped. The second one we wrote. That is 1.0. The 0.1 was scrapped. The 1.0 was good. Was the third estimate solver we wrote. Then I started working with Nikolai at Microsoft. We wrote the first E3 was so-so. The second one was much better. The third one even better, and keeps improving, right? Same thing for Lean. The first one was unusable. The second one, people at CMU managed to use, but was still horrible. Third one, the community starts growing. And now fourth one, we are super hopeful that will be way more successful than Lean 3. No comparison. It's night and day, the experience, everything.
So this sounds really hard to like. It wasn't none of the earlier Leans were a small amount of work. And some of them were fully, like Lean 3 I've used, and it's a fully usable interactive proof assistant. Mm-hmm. But you made the call to throw it out and start fresh. I think obviously you have a lot of experience that spoke to that and made it clear to you that was the right thing to do. But how confident are you when you make these calls to start fresh?
Yeah, sometimes, again, it's ignorance, right? You think, I want to build a programming language. We didn't know how complicated. I never wrote a programming... a proof assistant, when they say programming language, that's where I want to be able to generate efficient codes, right? Again, we thought, we can do it. This is not that hard. We can do it. It was basically Sebastian... right, we're together and he said, yeah, let's do it. And we started doing it. It was way harder than we expected. I mean, again, colleagues helped a lot. Simon Peyton Jones helped a lot, I mean, giving feedback, explaining things that we had to do to achieve good performance, right?
There's I'm not going to call it ignorance. I'm going to call it optimism and maybe naivete at the beginning.
Naivete. Yes, a good word.
to get started, right? But doing version 2 and 3 and 4 and sticking there, there must be, in addition to that, something else.
Yeah, I mean, being stubborn.
Yeah, well, that helps.
Yeah.
It's probably, the way Joey, I've never actually heard anybody describe Coq or any of these, like you did. It's a little bit like a game, and it actually made a lot of sense to me after having seen people do that. I wonder if there's part of that too. I mean, it's sort of fun, There's a reason people like Minecraft. You're slowly building things and doing them right, and sometimes you fail.
I've seen many people claiming that it's addictive, this proof assistant stuff. It feels like a puzzle, right? You're solving a puzzle. You can easily spend a lot of time doing it. Sometimes by testing, you say, Sebastian and I decided, let's formalize something in Lean just to see. We have a lot of experience using Lean as a programming language, but we don't spend a lot of time proving things using the system. But sometimes we do it just to test how comfortable it is, what are the pain points. And you can easily spend a lot of time. And sometimes you get into this stuff, you start doing it. And there's one thing that is quite different from programming, is that performance is not an issue, right? If your program type checks, you are done. When you are writing a program, you type check, you run, it sucks the performance, you have to refactor or redesign. This kind of thing doesn't happen when you're just proving, right?
It's when you're writing proofs about programs, and I assume it goes for math, you're in this very rare situation where you know what the outcome looks like, and you just need to get there. And then when you're done, the computer tells you you're done, and it's a pretty rare feeling in programming. To just like have someone say, yeah, you did it, it's right, like back it up, because for anybody that's spent time writing software, there's always this, and I'm sure for you on the developing Lean side all the time, there's this nagging, well, what if I got something wrong? What if there's a bug that I haven't caught yet? What if I missed a side of usability? There's so many lingering questions all the time, but inside of the proof world, you have this certainty that's a really nice place to live sometimes.
Actually, now that you mentioned that about usability, all these things, one thing that is really hard, I found really hard in a system like Lean, this is true for any programming language, with respect to Z3, is the Z3 has a clear spec, right?
Has a clear what?
Specification, what it should do, right? So you have a really well-defined language as input, and you should return true if the problem is unsatisfiable, or false, depends on how you decide. You just have to return. There are two possible outcomes: is unsatisfiable or is satisfiable, and here's the model that makes this formula true. Right, the spec is very well defined. Right, there is very little room for misunderstandings. But in Lean,
so it's you give me a formula, I'll tell you I'll tell you true or false more.
Yes,
it's a
exactly.
little more complicated than that, but it's
yes.
And you fully describe the way that the formula can be written in the first place as well.
Yes, exactly. There's a standard. There's a standard. So this part, you can focus only on the performance, on the procedures, or the fragments that are decidable. But in Lean, this is insane. It's like a programming language. People, there's no clear spec on the language should be, which features should be there. For instance, you add these interactive tactics, that's how you build proofs interactively. People have different ideas on how things should work. And user A wants this static to behave that way. User B wants the opposite. And one thing I learned after was really hard for me to learn that you can't make everybody happy, right? I mean, with Z3 it's easier to make everybody happy, but with Lean or any other programming language, it's really tough. I mean, language design, I think, the lesson I learned is really tough.
But through all that, I get the sense you want users. I feel like you want people to use Lean, so it hasn't scared you off.
No, So some users, I found that computer science users, I think, at least in my experience, is much easier to interact because they know how complicated things are. They have a better understanding, or more realistic expectation. They have used many programming languages before, especially programming languages that are on research from research labs. Right, they are not as polished as a programming language that's used in industry, right? For instance, I remember a colleague of mine saying, well, I have this ML compiler. I'm using it's a new one. If it tells me the error is here, that's all I want. So I don't want a nice error message. I don't want anything. Just tell me where it is, more or less. I mean, it's around here, right? That's the expectation, right? But if you're using something like TypeScript, your expectations are much higher, right? Or Rust. Rust is amazing. There are messages they produce, right? It's a lot of engineering care, right? But you need a big team, a lot of people to do that, right? I mean, when you're starting a new programming language, your error messages are usually crap, right?
And it's not easy. There's deep scientific questions basically, and how do I get good error messages? It's not like you just you didn't write a very good description of what went wrong.
Yes.
And I'm sure one of the things you've iteratively improved is figuring out how to track things better as information moves through the language. But
yes,
this is not a easy problem. So definitely like loads of credit to languages like Rust and TypeScript and how much work and how deep of an understanding of the language those engineering teams had to have to make that stuff work.
Yeah.
But it sounds like you want to make Lean into a language that's as usable as Rust or TypeScript. Is that an ideal end goal for you? We can talk about whether that's accomplishable.
Well, we can say it's a dream, right? I mean, I think both Sebastian and I would be extremely happy if we have something as user-friendly as Rust, right? And also, if you want to, it's impossible for two people to build something like Rust. You need engagement from the community, right? And the way to get engagement is to start making something is in this path, right? That can be extended. People can work in different modules. For instance, a colleague of mine from Microsoft starts helping Danny Fabian. It's great, right? I mean, we need more people like him from outside. If you want to be as big as Rust, Rust has a lot of people, right, helping.
I imagine the starting point there is just starting to use the language for something. And if that's the case, if people are listening and wondering, well, I guess the question is who should consider just jumping into Lean right now? Lean 4 especially.
People that's the first thing, I think people that are excited about new programming languages, want to learn dependence types, I think they would benefit right now using Lean 4. They can have a lot of fun. I think right now, if you have you're interested in formal mathematics or program verification or proof assistance, you could benefit. But if you're a programmer, I think right now the main benefit is if you want to learn dependence type theory, if you're excited about these ideas, I think Lean is a cool programming language to try.
But what I'm hearing there is you don't already need to know dependent types. Lean would be a nice way to start, basically, and through interacting with the Lean community.
Yes. But I think I have a bias towards dependent types because I think it's really beautiful. I mean, for me, I was so excited when I started learning these things, and I think many of your listeners, if they start learning, they will also be super excited.
I think I'm gonna finally go and check that tutorial we mentioned after this.
It's and I think that even starting to dip into what dependent types is going to be too much of a diversion, unfortunately. Mm-hmm. But yeah, I agree completely. And I mean, the most basic Lean programs, you don't need dependent types, and you can start programming and learn as you see the need, basically, which I think is a really ideal way to introduce people to new topics, is to say, well, like, you program and maybe you sort of see this thing that you wish you could do, and you ask, how do I do this? And you go to the Zulip chat, for example, I found to be a great place to interact with a lot of people who are really eager to help. And you say, how do I do this? And then all of a sudden they introduce this concept, and you say, okay, well, I really care about this because I was already trying to do the thing it accomplishes. And all of a sudden you've started learning, you've taken your first step. I find that approach can be so much more effective than, like, I'm going to crack open the book on dependent types and sort of start on page 1. As soon as people can dive in, usually, it can be really helpful to just understand why, rather than just learning for the sake of learning, I guess.
Well, with that, and for me at least, I think, the project or what they're using it for, even if it's primarily for learning, what sort of types of projects do lend themselves better to doing this, or what sort of little toy examples or something larger. I wonder if you have any thoughts on that.
There are things that would be really nice now if people want to write extensions to Lean, right? That's one thing that's would be super exciting. People start using Lean and they start using Lean to extend Lean itself. I think this can be done now. It would be super useful for the community, right? There are other projects like it's Galois. I mean, Joe Hendricks had this demo of the robots that was super cool. Right, he's basically controlling a robot using Lean. Right, he has a blog post now, a super exciting project. This kind of project can be done. Right, Lean is easy to interface with C. Right, since projects that you need to call to perform I/O with the external world, or call your APIs that you have written in a different programming language. All this kind of project is possible right now. Right. I can tell you about projects we have at Microsoft that are using Lean. For instance, Daniel Selson has a project called the IMO Grand Challenge. The goal is to get a gold medal in International Mathematical Olympia. Right. And for extremely hard, this math competition for high school students, but the problems are really tough. I think I would get a 0 if I try to compete. You have to train for this kind of stuff, right? There are a bunch of tricks, and if I go there today, I get 0, right? So, maybe 1. I get 1 problem. But he wants to write a system that can solve these problems automatically. And one idea is that you have to write domain-specific automation, right? There are many techniques that you can. They are not general purpose. They are very specific to a class of problems. And he's doing this stuff using Lean, right? Another thing that we're excited about is using Lean, using the proofs for optimizing tensor computations, right? You have machine learning is a big topic now. You write these tensor computations. That's abstractly is a bunch of matrix multiplications. Right, and you want to optimize this kind of program, right? And proofs might help. That's one kind of project that we're excited about.
For my learning on that one, what makes the way Lean does things more just better for those sorts of optimizations?
Oh, because you can not just write your tensor computations, but you can write in-link programs that manipulate your programs that are performing the tensor computations, right? And so you can write in-link a program that treats your program that you want to optimize as data, right? You're writing a meta program that treats your link programs as data and tries to optimize it. He may do like a search over the space of possible optimizations and find an optimization that you would never think of or would be too time-consuming to write by hand, right? That's the kind of possibility that's attractive in these worlds, right? To write programs that search the space of solutions, right? The space of programs.
That's amazing. I would love, frankly, I think, I don't know, maybe it's just me, but like having a very simplistic tutorial that walks through an example like that, especially as you said, machine learning is in the news, but
yes.
It will be very interesting.
Yeah, it's a good idea.
Did you have any other examples that you wanted to walk through?
Let's see.
We don't have to. I just wanted to make sure I didn't interrupt you.
No. These were the main two examples, the two applications that we're considering internally at Microsoft. But in the math community, they have many, right? I mean, if you go to the Zulip channel, now they have this condensed mathematics sub-channel there in the link for Zulip channel. And they're trying to formalize these results for this famous mathematician, Peter Schulze, I think is his name. And they are super active there. If you're a math person, probably are going to find this. I don't go there. I don't even understand what they are doing. I mean, they try to explain to me why this is relevant. I don't get it, but I trust that they know what better, right? I mean, they tell me that's really important, but I don't really understand the math there.
If they're doing very important things and you're working on the language and the tools,
yes,
must be a little pressure too.
For sure. I mean,
no pressure.
Yeah.
So we're running a little low on time, but I wanted to ask a final question, which is, what do you view the most successful version of Lean as being? Where do you want Lean to go? I've heard that maybe you're thinking about integrating Lean with Rust a bit.
Yeah. I mean, we want to have a programming language that you can generate efficient codes, right? I mean, it's high level, but you can use the proofs to optimize to generate efficient codes. With support for metaprogramming, right? You can write programs that transform your programs, right? You can prove small properties about your programs. Big properties is your decision, but you have this option if you want. And you want to have this integration, this user experience for systems like a system like Rust provides, right? That's for sure is one of our goals. You mentioned integration with Rust. Yes, we definitely want to do that. I think Lean is very compatible with Rust. Lean is a pure functional programming language, but it doesn't use generation or a tracing garbage collector. It uses reference counting. It's very compatible with the Rust system, right? One of our goals would be to have a way to call Rust functions functions written in Rust that is really convenient for the user, right? You want to call some Rust function, it should be super easy to do in Lean. That's one of our dreams, to have this kind of capability. Why do we want that? Because Rust is getting really big, many libraries. You could use all the libraries they have developed, right? That's was one motivation. It's easy to use. I don't know if you have used Rust, but the package manager is awesome, right? We have the ambition to have a package manager like Cargo, right? And being integrated would be great, right? Because if you could even feel like that, Rust allows you to achieve C performance now, right? But most of your programs don't need to achieve C performance, and Lean is much easier to program than Rust, right? It's much higher level. It's like the feeling for, if people that are familiar with Haskell, Lean has this Haskell vibe, right? When you're programming, you have all these goodies that you have in Haskell. It's more, at least in my point of view, way more flexible than Rust. But Rust has the core performance, right? You can achieve really high performance with Rust. And exciting combination is, okay, some parts of your program you need extreme high performance to write in Rust. You can integrate smoothly with Lean. The rest you write in Lean, right? Then if you want assurance in some part of the code, you write in Lean and prove it's correct in Lean, right? I think it's a nice, would be a nice experience to users, right?
So it sounds like everything, there's the vision where everything works nicely between the two languages, and maybe I do just a package import and
yes,
I maybe know that it came from Rust or Lean, but I don't have to worry about it so much.
Yes,
it
exactly.
just works well with whichever type system I'm using. It seems like it would make a lot of sense for the Rust community, where there's clearly a huge appetite for correctness.
Yeah, and if a Rust user, it's much easier to get a Rust user excited about Lean than a C user, right? Rust is already using a functional like concepts. You have lambdas, you have all this stuff, lets, and so on. It's much closer to Lean than C, right?
So if you're a Rust user who's looking to take correctness a little farther, maybe you are an ideal early adopter for.
Oh yeah, for sure. I mean, you're going to find many ideas in Lean came from Rust, right? Cool. Yeah. You're going to find some keywords that are similar. For instance, we have this let mutes in Rust for mutable variables. We have that.
Nice.
Yeah.
So you'll be able to carry across some of the things you've learned from Rust and make use of those directly in Lean.
Oh yeah, for sure.
That's excellent. Well, I think that's about all the time we have. Thanks so much for joining us, Leo.
Yeah, it was super fun. Thanks for the invitation. It was my first podcast and it was super fun.
Ours too.
Yeah.
You couldn't tell? It was a lot of fun talking with you, Leo. Thank you.
Thank you. Thanks so much, guys.
All right. This was another episode of Building Better Systems. Join us again next time.